New type of threats emerging in the early 70s induced a new wave of research in the Soviet Union, which led to the development of a new homeland air defense missile system, as well as to the Army and the Navy. This ultimately became known as the venerable S-300P family and some others. Let's see its history from the beginning. Here comes the scene engineering of the S-300P. In December 1966, following the successful testing of the S-200 Angara system, a request for proposals has been issued by the Military Industry Committee. The various Soviet design bureaus had to propose a new generation air defense missile system. This time, this would be a joint system for the Homeland Air Defense, for the Army, and also for the missile cruiser ships of the fleet. The future system had to be multi-target channel capable and at least medium range. Also, there were further requirements specific to different branches of the armored forces, which also had to be considered during the development. The Soviet defense industry was influenced by the same approach what the Secretary of Defense Robert McNamara took in the United States. That cost-cutting measure led to the TFX program and to the F-111 plane, which was intended to be a common multi-role air fighter for the US Air Force and the US Navy. The F-111 did not fulfill the original objectives, but at the end of 1966 it has not yet been disproved the original concept. The Soviets sympathized with the same approach that seemed cost-effective at the time. The expectations of different branches of the armed forces were as follows. The main threat for the Homeland Air Defense was aircraft flying at low altitudes and the terrain-following cruise missiles, which were developed later. The S-25 Berkut system around Moscow could not deal with either of these, nor could the subsequent SA-75 Dvina and S-75M Volkov families. The minimum engagement altitude of the S-75M system was reduced to 100 meters only in 1970, which was still insufficient against the rain-following targets. Increasing mobility and reducing deployment time was also expected. The main system components had to be installed on a self-propelled or tow vehicle chassis. The typical 1-2 hour scale of deployment time of the S-75 and S-125 had to be reduced to just 5 minutes. Among the requirements was that the new SAM system must have more than 5 target channels to surpass even the largest 5 missile battery capable S-200 site. In addition, the missile was specified as a single-stage design. Anti-ship and cruise missiles were the main forecasted threats to the fleet. The low altitude or even anti-sea skimming capability was predictable. Due to the size limitation of the ships, vertical missile launch was specified with cold start method because of the safety reasons. It was not allowed to design such a system where the rocket engine of the missile is started inside the missile container. The use of liquid, volatile and toxic propellants was discarded, solid propellant had to be used. I would like to add that every branch of the armed force would have given up liquid propellant missiles without hesitation due to their cumbersome operation. The Army specified the new system with self-propelled nuclear, chemical and shrapnel-protected tracked vehicles. The new system shall be capable of intercepting the maneuvering Pershing ballistic missiles in its terminal phase. Of course, it had to be suitable against highly maneuverable fighter jets and fighter bombers, which using self-protection jamming even at low altitude. As time passed, it seemed that the idea of the joint SAM system is not the path to the success. By this time, it had also become clear that the F-111 as a joint aircraft platform had failed. The specification of the new Soviet SAM systems were way too different for every branch of the armed forces. This had to lead to the changing of the original concept in 1969. After Dmitry Fyodorovich Ustinov followed the discussion, then the future defense minister decided to set up a conference with all the involved branches. After taking in and correlating all the different viewpoints, he decided that 2 main versions should be developed and they should also be separated functionally from each other. The main targets of the S-300P complex for the Homeland Air Defense and the naval S-300F systems were low-level targets and sea-skimming anti-ship missiles for the latter. Of course, manned planes and high-speed, high-altitude targets also had to be considered. The focus of the army for the S-300V system was intercepting the American Pershing 0A ballistic missiles, which were deployed in Western Europe at the time. Later, the capability against the Pershing II missile was also specified, but this ballistic missile did not even exist in 1969. Capability against low-flying or terrain-following targets also was a demand, but with higher mobility what the S-300P would have. Essentially, the deployment time had to be same what the Kub NATO code SA-6 and the Krug NATO code SO-4 had already achieved in the 60s, 5 minutes deployment time following a stop. So, the one-letter designation difference between the S-300P and S-300V can be misleading due to the vast differences in between them. These are completely different SAM system families. Even though the original idea was that at least the main items should have been the same, with the same missile guidance principle, as we will see later, not even this basic goal was achieved. From the viewpoint of the Homeland Air Defense, the goal was to create an air defense system capable of shooting down targets flying at 25 meters of altitude only, even if these targets are deployed in a saturation attack. Therefore, even a single missile battery had to be designed with multiple target channels, more exactly 6 was specified. This figure originated from the 5 missile battery S-200 system. To surpass the predecessor, the new system had to be designed with 6. Besides this, at the minimum range of the S-75M Volkov had to be achieved, which was 55 km against subsonic targets flying at medium-high altitude. Combining these requirements, the new SAM should ultimately replace the S-75M Volkov, S-125M Neva and the S-25M Berkut systems around Moscow. However, the long-term goal was even more ambitious, aiming to replace the long-range S-200 with the S-300P family. For this, the 300 km maximum engagement distance of the S-200D Dobna had to be achieved with further developments. This was anything but an easy task. Because of this requirement, the S-300P system was developed incrementally to achieve this very ambitious goal. The Soviets did not try to solve the gigantic task with one large leap. A little spoiler here, the 300 km of range was finally met by the S-400 system with the 40 N6 missile. Yes, that's right, the S-400 is also an S-300P variant, it just got a nice little new marketing label. But at the time nobody guessed that achieving the long-term goal would take about 40 years. The end of the story that the introduction of the S-300V1 SAM happened 5 years later compared to the first S-300PT battery, which was fielded in 1978. The V1 variant had the capability to intercept ballistic missiles with a range of 300 km. The fully capable S-300V version, which was designed to intercept the Pershing II ballistic missiles, was completed 10 years later, only in 1988. Eventually, even the fleet managed to design the S-300F with a unique fire control radar that not only takes into account the ship's rocking, but also completely seals it off from the corrosive saltwater. Moreover, not even the missile storage container was interchangeable with the S-300P variant, even though the missiles were identical with the land-based variant. The 3 different branches of the S-300 family essentially had only 3 things in common. They all used solid propellant missiles, digital computers and phased array radars. From the American point of view, the story starts with the appearance of the S-200 Angara SAM system. It became obvious that further increasing the speed and altitude of the manned bombers is pointless and a fruitless effort. With the realistic technical and budget frameworks, it was practically impossible to build such a fast, manned aircraft what could deal with the S-200 by only its high speed and high altitude. Not even the B-70 Valkyrie, the Mach 3 capable bomber, could that. But something had to be done. In the first step, the B-52 bombers got a longer spear, so to speak. The free-fall bombs were replaced by the AGM-28 Hound Dog missile from the early 60s. A B-52 could carry a pair of them under the wings. The launch distance of the missile reached 1000 km at high altitude, so it could be launched far outside the engagement zone of the S-200. The missile carrier bombers had significantly increased chance of survival even against the interceptors of the Homeland Air Defense. However, despite the Mach 2 speed of the missile, it could be downed even by the S-75 Vina or S-75M Volkov SAM systems. So the Hound Dog as a target was not a qualitatively challenging thing. Using a slightly false analogy, instead of a Mach 2 capable B-58 manned bomber, the B-52 got such a new toy which did not have to fly there and back to the target. It was unmanned, and instead thousands of kilometers of range, 1000 kilometers was enough. The AGM-28 is essentially an unmanned and downscaled B-58, which made it possible for the B-52s to carry them. Against the single target channel SAMs, it was possible to attempt a saturation attack even with only 2 missiles per bomber. The AGM-69 SRAM was fielded also from the late 60s. The SRAM was essentially an air-launched semi-ballistic missile which was able to fly at an almost ballistic trajectory at high altitude, as well as flying with a low-altitude attack profile with a reduced range. The B-52 could carry 20 of these thanks to its smaller size compared to the AGM-28. The cost of this insane firepower was that, even at high altitude, it only had 200 km of range. However, lots of missiles could be combined with low-altitude flight following a quick climb to saturate S-200 systems and break its area denial capability. In the end, the ultimate solution to the Cold War was creation of such a missiles that could be launched at a lower altitude from a greater distance. The goal was to design smarter missiles instead increasing the speed. From the very end of the 70s, this new threat appeared in the form of the AGM-86 OLCM, which can be launched from the air. That followed closely by the BGM-109 Tomahawk, which can be launched from land and ships, and later from either submarines or land-based vehicles too. The platform for the AGM-86 could be the other B-52 and the new B-1B intercontinental bombers. These cruise missiles were designed with the revolutionary TERCOM guidance, which enabled them to fly completely autonomously using autopilot, following the terrain at a height of 30 meters. The B-1B would have approached the Soviet Union at a low altitude of 60 meters, also using terrain-following radar. Due to the low-altitude attack profile and the gas turbine engine, their maximum speed is only 800–850 km per hour. But if they are so slow, why did they pose a radically different threat compared to the previous weapons? Thanks to their small physical size, the cruise missiles have a smaller radar cross-section of around 0.1 square meter, which makes their detection more difficult. Flying at an extremely low altitude, 30 meters over flat terrain, they can approach their targets even lower. This seriously limits the engagement zone of SAMs, since they cannot detect targets flying below the radar horizon. In addition, it is not an easy task designing a proximity fuse which works reliably so close to the ground or water surface. The range of the terrain-following cruise missiles reached 2000 km, which means that they could be launched way outside the engagement zone of any SAM systems. These were able to reach Moscow and most of the territory of the Soviet Union, even they do not fly following a straight line to the target. They could keep a safe distance from known air defense position wherever possible by flying on a pre-planned route. The Homeland Air Defense fighters, like the MiG-31, should have shot down most of the cruise missiles, not the S-300P SAMs. Of course, it would be the best if the bombers were shot down before launch their payload, but the chance of the latter was rather slim. The area defense was possible only with the MiG-31 fighters, which had larger engagement zone flying at high altitude. The radar horizon was not a limiting factor. However, the existence of the MiG-31 Foxhound did not mean that SAMs should not deal with the cruise missiles, which bypassed the combat air patrols of the fighters. The consequence of the appearance of the terrain-following cruise missiles that the area denial capability provided by the S-200 even against high-speed targets ceased to exist against this new kind of targets. The S-200V Vega system could shoot down targets up to 1200 meters per second speed, which is Mach 4 up to 180 km range and flyby distance. No matter how slow the cruise missiles were compared to an AGM-28 or a B-58 bomber at high altitude, thanks to their extremely low flying altitude, practically all previous efforts of the Homeland Air Defense were nullified. Even if the Soviets could design a new air defense system capable of defeating such low flying targets, the radar horizon sets a very serious limit to the engagement zone. Even in an idealized case, the edge of the zone was only 38 km away, even though the targets were slow. Therefore, the targets to be defended had to be deployed with missile batteries in the good old ring formation, as was previously necessary for the Berkut, Volkhov and Neva. The big difference was then about an order of magnitude higher cost per missile battery. Replacing the 8,500 km long barrier air defense line, what was previously created with the S-75 and Volkhov complexes, would have been impossible financially. The S-300P family replaced the S-75 and S-125 families only at the most important cities and key military installations that had already been protected. A B-52 bomber could launch 8 missiles from its internal weapon bay and an additional 12 from under its wings. A B-1B Lancer could launch up to 16 cruise missiles within minutes. The Soviets had to prepare the air defense against lots of incoming targets in a small area within a very short period. It was advisable to attempt the breakout of the Soviet air defenses with a saturation attack, preferably minimizing the available time to the SAMs. Even if the Soviets had tried to solve the task by mass deploying the S-125M Neva systems, it would have been a hopeless attempt no matter if it had a low-level capability. But it had only a single target channel and it was not a medium-range SAM. Essentially, this path led to the demand for the S-300P. During the development of the S-300P family, experience from the Vietnam War was also taken into account, which can be summarized as follows. The opponent has the air superiority, the goal is to defend an area, but in certain cases it may be necessary to use hit-and-run tactics, which was also used in Vietnam. The latter could have occurred rather in case possible proxy conflicts between the USA and Soviet-supported countries. In the countries of the Warsaw Pact, in peacetime, the S-300s would typically have been deployed in fixed firing positions, but in the event of war, they would have been deployed on field for auxiliary sites. For this reason, it was necessary to install the main component of the system on self-propelled wheeled vehicles. The S-300P partially inherited the structure and organization of the S-200, but missile batteries and the commanding unit were no longer static, they were mobile. The original specification demanded 5 minutes readiness time from stopping, but with certain limitations, see later. Multiple target channels were needed, but not only because of the possibility of a saturation attack with cruise missiles. As a side effect of a system having multiple target channels, anti-radiation missiles also can be downed, besides the other incoming targets. Thanks to the multiple target channels, it is not possible to suppress the SAM with some or even a single AGM-45 Shrike for a short time, but happened many times in Vietnam. This feature was ensured by the passively electronically scanned array fire control radar. Several types of radars were required for the system. Each missile battery had to be equipped with a multi-target channel capable fire control radar with a phased array antenna system. Each missile battery had to be equipped with a continuous wave, low-altitude 360-degree target acquisition radar to detect the terrain following targets. The missile batteries had to solve this task on their own. It is not possible to achieve the goal with a centralized radar because of the distance between the missile batteries. Regardless of the long nominal detection range of a radar, the radar horizon and topography limit the detection range against low-altitude targets. The low-level radar had to be at the same location as the missile battery. 360-degree coverage was specified against medium and high-altitude targets with a long-range target acquisition radar as usual, but with much shorter deployment and readiness time. Only the regiment or brigade shall have this long-range target acquisition radar, just like the S-200 system had the P-14F, which served more than one missile batteries but on the same site. This means that 2 to 6 missile batteries have only one long-range target acquisition radar, which is part of the command system of the regiment or brigade. In contrary, each S-75 or S-125 missile battery had its own long-range target acquisition radar. The missile had to be single-stage design with solid propellant. Instead placing the missile on launch rails, the missiles shall be loaded and stored in a hermetically sealed container. The diagram shows a regiment with 4 missile batteries, but only with its main equipment. The missile battery in the red frame has 4 launcher systems, the latter are in blue frame. 4 missile batteries and the commanding system from a regiment, this is inside in the green frame. The logic is the same for the S-300PT, but the launcher vehicles are not self-propelled, neither the RLO, the long-range target acquisition radar. All S-300P versions, as well as the S-400, have the same structure, apart from minor differences. Only the export S-300P MU version differed from this, but we will return to this later. What are the main elements of the system? The command system consisted of 360-degree long-range target acquisition radar and the regiment brigade command post. The radar is the 5N64 RLO, NATO codename Big Bird. The command post is the 5K56 PBU. The command system served from 2 up to 6 missile batteries, each with 2 radars. One low altitude 360-degree capable target acquisition radar, the 5N66 NVO, NATO codename Clam Shell, which was installed on a mobile tower. The other radar is the target illuminator and guidance station, the 5N63 RPN, NATO codename Flaplid. Each missile batteries had 4 launcher systems. Each system consisted of 3 towed or self-propelled launcher vehicles and an F3 cabin that controlled the launchers. The launchers of the S-300PS variant were self-propelled. Keep in mind the 3-letter short names of the radars, because for the sake of simplicity, we will only use the shortened form for the rest of this video. So once again, the 2 target acquisition radars are the RLO and NVO, and the guidance station is the RPN. In accordance with the design requirements, the missile batteries of the S-300P system were assigned into air defense regiments or brigades. A regiment consisted of a maximum of 3 missile batteries with 1 command system, a brigade of 5 or 6 missile batteries with 1 command system. Before the detailed presentation of the main equipment of the S-300P system, it is necessary to know the background of the development and installation conditions. The threat posed by the terror-following cruise missiles were so imminent that, contrary to the original plans, the installation of a less mobile, trailer-mounted version began in 1978. This was the S-300P2 version, NATO codename SA-10A. Between 1978 and 1985, 86 S-300PT missile batteries were manufactured to replace the S-25 Berkut system around Moscow with the installation of 56 missile batteries. One S-300PT battery replaced 1 Berkut regiment. The remaining 30 missile batteries supplemented the air defense of 5 important cities: Minsk, Gorky, Dnipropetrovsk, Novosibirsk, Riga, and 2 shipyards, Severodinsk and Nikolaev. Since the system was manufactured with towed vehicles, instead of the 5-minute installation time, only 2 hours were available, similarly to the S-75M Volkhov. The successor of the S-300PT was the mobile S-300PS Volkhov M6, NATO codename SA-10B. It was produced from 1983 to 1991. The variant got the Volkhov as name to deceive the Western intelligence. It had nothing to do with the S-75M system. From the 140 manufactured missile batteries, 20 units formed the defensive ring around Leningrad, organized into 5 missile regiments. The remaining 110 missile batteries replaced the S-75M Volkhov and S-125 Neva systems in the most important settlements. Typically, some batteries were deployed per settlement. The most noticeably changed compared to the PT variant was that the launchers were now installed on a self-propelled chassis, just as the fire control radar, the RPN. However, due to their size, the low altitude and long-range target acquisition radar of the command system remained on a towed chassis. However, they were not disconnected in a deployed state either, because the electric generator was on the towing vehicle, forming a single unit. Since the ability to travel on public road network was a requirement, the semi-trailer solution was chosen. A very long oversized chassis, similar what was designed for the Topol ballistic missiles, was not an option. Both the command system and the missile battery had a geodetic surveying vehicle, since the batteries could be deployed on the field too, not only in fixed firing positions, as happened with the PT variant around Moscow. The basic structure and capabilities of the PS version in the deployed state with the same missile type did not differ from the PT version. Their main characteristics, the engagement zone, target speed, etc. were the same. In fact, the self-propelled vehicles were necessary to achieve the originally specified short deployment time besides other upgrades. In an S-300P missile battery, every main component were connected to each other by cable. The telecode radio connection was only available between the command system and the missile batteries. As an exception to this, there may have been a cable connection between the command system and the missile batteries, as a legacy of the S-25 Berkut system in the ring around Moscow. For the S-300PS variant, within the command system, telecode or radio or wide connection was available between the RLO target acquisition radar and the PBU command post. It had telecode radio link between the command system and the RPN fire control radar of the missile battery. Within the missile battery, the NVO and the RPN were connected via cables. The RPN and the launch platoons were connected to cable or radio telecode, but only via the main launcher of the 5P85S vehicle. The two auxiliary launchers of a platoon, the two 5P85D vehicles, were connected to the main launcher only via cables. The command system of an S-300P has paramount importance regarding the potential and capabilities of the missile batteries. The 5N83 command system consisted of the following main equipment: 5N64 RLO long-range target acquisition radar, NATO codename Big Bird, 5K56 PBU command post. For the missile batteries at medium and high altitude, the RLO, the Big Bird radar of the command system detects and designates targets in normal operation. The designated target coordinates are forwarded from the PBU command post to the missile batteries. It is important that at medium and high altitudes, if the missile batteries do not perform an independent target acquisition with the RPN, then they can only track the targets designated and forwarded by the PBU and nothing else. The command post can share the complete radar picture with the missile batteries. The command post of the regiment or brigade is semi-automated. It prioritizes the targets for the operator and recommends a missile battery with an optimal location to destroy the target. Because the missile batteries deploy about 25-30 km from the command unit, the RLO is not able to provide the low altitude situational awareness to the missile batteries. This is despite the SDC feature of the RLO, which makes possible to track targets at very low level at the edge of the radar horizon. Simply the distance between the missile batteries and the command unit is too large, the radar horizon of the RLO is too close compared to the RPN of the missile batteries. The missile batteries have to detect the terrain-following targets by themselves with the NVO radar. The consequence of this is that without the RLO, the missile battery have a very limited medium-high altitude situational awareness. The RPN and the NVO radars are not designed to perform independent target search in a large airspace in 360 degrees. The NVO is physically unable to search in the zone above the terrain-following targets, since its beam width is only 1 degree, even though it rotates at high speed. On the other hand, the scanning speed of the RPM is insufficient to scan even sector search mode a larger airspace. There are several workstations at the command post. The PBU can share target data for all 6 missile batteries of the brigade. The command post can receive data from the adjacent S-300P command post via digital data link connection using the telecode radio connection. However, the missile batteries are only connected to their own command system. Even the missile batteries within the same regiment or brigade are not able to share target data with each other. Providing the RLO radar to each missile batteries would have been overkill and would have made the system insanely expensive, as we will see later. Compared to the S-75 and S-125 systems, the S-300PT and PS are different. Only the common system have long-range, medium and high-altitude target acquisition radar, the 5N64 RLO. The radar was designed to detect targets flying at medium and high altitudes, as well as the Lance and Surgeon type ballistic missiles. The coordinates of the detected medium and high altitude targets by the RLO are designated and forwarded to the missile batteries via the brigade's command post during normal operation. This does not mean that a missile battery cannot perform independent target search, but it can only do under serious limitations with the RPM fire control radar, see later. The RLO was manufactured in 3 versions considering the S-300PT and PS variants. The first was the 5N64K container version from 1978. The 5N64KV version is equipped with a digital SDC mode, which made suitable for detecting targets flying at low altitude on the edge of the radar horizon. This was produced from 1981. And lastly, the self-propelled 5N64S version was deployed from 1983 for the PS variant. The deployment and readiness time of the RLO was 2 hours for the K and KV RLO variants and only 5 minutes for the S. The activation time of all 3 types in deployed position is 3 minutes. In case of the S variant, all the 3 cabins are installed on a towed trailer, which is towed by a MAZ-74-10 vehicle. The parts of the RLO are the following: F6 two-sided phase array antenna and rotating structure, F7 transmitter and receiving cabin, F8 processing and control cabin. The F8 cabin was in a separate container for the PT version, but the radar antenna could unpack itself from storage position. Even the first variant was capable of doing that. Craning was unnecessary, in contrary to the fire control radar of the S-75 and S-125 SAM systems. For the S-300PS variant, 3 cabins of the RLO are mounted on the same tow chassis. The detection distance of the RLO against the MiG-21 at medium and high altitudes is 185 km. Against a terrain-following cruise missile with a radar cross-section of 0.1 square meter was 105 km, but only if the terrain elevation makes possible the detection. For this, the radar must be higher than the target, since the radar horizon is about 31 km away even on flat terrain. Interestingly, the SDC mode was necessary for the long-range target detection too. At 180 km distance, targets flying relatively low and at medium altitude are barely above the radar horizon. The effect of the ground reflection had to be filtered out. The price of the SDC mode is the 20% smaller detection distance, but at least the detection zone reached the radar horizon at low level. The displayed maximum distance of the radar is 300 km and the maximum target altitude is 50 km. The RLO operated in the decimeter wavelength range in the S waveband. A unique feature of the Big Bird radar that is built up from 2 antenna systems. One side of the antenna structure scans the airspace to detect new targets, while the other side performs the second measurement required to track to detect targets. This operational principle reduces the time required to track new targets. The scan is performed electronically in vertical direction. The RLO has 2-phased array mirror reflector type antenna system. The 2 funnel-shaped transmitters sends the pulse to the reflective phase array antennas, while the antenna structure is continuously rotating. In a much shorter time compared to the time of rotation, the phase array antenna scans the airspace with its pencil beam in vertical direction. In azimuth, left-right direction, the radar is mechanically scanned by the rotation of the antenna structure. The rotation speed of the antenna is 5 revolutions per minute, so the radar picture is updated in every 12 seconds up to 300 kilometers. The NATO codename of the radar refers to the appearance of the antenna structure, which from a certain angle resembles a bird spreading its wings. In elevation, the radar performs the target acquisition scans between 0 and 14 degrees, but targets have been already detected can be tracked up to 55 degrees. Basically, the RLO scans the airspace long range down to the radar horizon, but even if the target flew quite close following the detection, it didn't lose the track of the target. If the task is detecting short-range ballistic missiles, the RLO is set to a fixed direction, the antenna structure does not rotate, it performs sector search only. The target acquisition scan is performed with plus-minus 60 degrees in azimuth and between 0 and 20 degrees in elevation. Essentially, the task is to detect missiles climbing from below the radar horizon. Targets that have already been detected can be tracked up to 55 degrees, similar to the 360 degree scan. The RLO also scans electronically in azimuth when in sector search mode. The radar uses coherent quasi-continuous waveforms for target detection and linearly modulated quasi-continuous waveform for target tracking. Stationary targets with 0 radial speed are filtered out with digital SDC mode. This is available to the K and S RLO variants. Quasi-continuous signals means that the continuous sinusoidal signal is interrupted, but the pulse length of the transmitted pulse is many times longer compared to what the conventional coherent pulse radar would use. However, the transmission of these longer pulses occurs on an order of magnitude more often compared to the conventional coherent pulse radars. Thanks to this, the peak impulse power of the transmission can be reduced by an order of magnitude, while the average power within a single duty cycle remains the same. Despite this, the detection distance is the same to a conventional radar, operating at 10 times higher peak impulse power. Heat load caused by the microwave energy passing through the phase shift elements can be reduced. To measure the target distance, a frequency modulated signal is required, where the frequency is continuously and linearly changed within a single pulse. The features of the Big Bird radar made the command system so expensive that the two vehicles of the command system cost just as much as an entire missile battery without missiles but with two radars. For the detection of terrain-following targets, the missile batteries have a dedicated low-altitude 360-degree scanning continuous wave target acquisition radar. This was the 5N66M NVO NATO codename Clam Shell. The NATO codename to the NVO is also derived from the shape of the antenna. Since the radar horizon limits detection range against low-altitude targets, the radar antenna is installed on the top of a mast. Interestingly, the NVO was not originally developed for the S-300P system, but it eventually became the essential part of the low-altitude capability. This is the reason of the letter M in its designation, because it was already a modified version in accordance with the needs of the S-300PT. The special feature of the radar is that it is mounted on a 25-meter high mast. The designation of this tower structure is the 40V6M. The mounting was necessary to detect the terrain-following cruise missiles as early as possible. Thanks to the higher elevation of the radar antenna, compared to a radar with elevation of 5 meters, the low-altitude detection distance increased from 31 km to roughly 43 km in case of perfectly flat terrain, considering 30-meter target altitude. This doesn't seem like much of a difference, but against targets with 20-25 km flyby distance, it significantly increases the time available for shooting them down. As the NVO is physically situated higher above the ground than the RPN, it is able to predict any terrain-following cruise missiles well before the RPN could physically see them. This provides significant preparation time to the RPN and allows the missiles to be prepared. Also, by the time the cruise missiles emerge above the radar horizon, the RPN is already focusing on the target area. This helps to achieve a quick lock-on launching of the missiles, which can happen mere seconds after the lock. Due to its continuous wave operation, the antennas of the RVO are similar to the RPC, the continuous wave target illumination radar of the S-200 system. The antennas are rotated by 90 degrees due to the different role, the low-level target acquisition. The antenna structure itself and the necessary equipment are mounted on the top of the 40V6M mast. The transmitter antenna is located at the top, the receiver is located at the bottom. The total weight of the entire structure which the mast supports is 11 tons. The size of the equipment box behind the radar antenna is comparable to the size of the driver's cab of a crash truck. The NVO is not a small and light piece of equipment, while the antenna rotates at a high speed. The rotation speed of the NVO antenna is 20 revolutions per minute. The radar picture is updated in every 3 seconds. The rotation speed of the antenna clearly shows how important it was to reduce the reaction time of the SAM system. The NVO is only suitable for detecting incoming targets. There was no point in detecting receding terrain-following targets. The fire control radar had to track them long before they would become a receding target. Incoming targets are detected with a monochromatic continuous wave signal. The distance is also measured with a linear frequency modulation, as the RPC of the S-200 did. The radar transmits a beam of a 1 degree wide in elevation, because the goal is to detect only low altitude targets. The maximum display target distance is 120 km, the system can track 15 targets. The average transmitted power is 1.4 kW. For comparison, this is half of the RPC of the S-200 Vega system. The NVO operates in the centimeter wavelength in the C-band. The 40V6MD mast became available to the NVO and for the RPN as well from the mid-80s. This now not actually means a new mast, but a new attachment, increasing the height of the antenna from 25 meters to 39 meters. The additional 14 meters increases the detection distance, considering a flat terrain, to 48 kilometers from 43 kilometers. If the RLO, the Big Bird radar, is the brain of the S-300P, then the 5N63 RPN NATO codename Flap-Lead radar is the intelligent fist of the system. The codename of the radar, Flap-Lead, comes from a physical similarity. Between the storage and operating positions, a hydraulic cylinder extends the antenna visually in a similar way as the top of the water bottle opens. For the PT version, the target illumination and missile guidance radar were located on a separate trailer. The PS version got the self-propelled vehicle, the radar antenna and the fire control cabin were mounted on that. Compared to the previous SAM generation, the RPN was designed with a true type phased array antenna, which replaced the old mechanical scanning. In short, this is called PESA, which means Passively Electronically Scanned Array. The antenna structure can be rotated 360 degrees. The PESA working principle was essential to achieve the multi-target channel capability, as it is necessary to implement target illumination and missile tracking with a single radar. The essence of the PESA antenna-equipped fire control radar is that the azimuth and elevation angle of the pencil beam, formed in a rapid succession, can be anywhere within the scan zone of the RPN. 2 consecutive beams can be even on the opposite edges of the zone. So if the RLO target acquisition radar has already provided the bearing, distance and even speed of the targets, the fire control radar only has to scan the airspace nearby to the targets to achieve continuous target tracking. The rest of the airspace does not matter from the point of view of missile guidance, so it is just a waste of time to scan the whole airspace with a fire control radar, because the RLO and the NVO do the target acquisition. The PESA radar antenna array operates on the principle that the transmitted electromagnetic wave is electronically deflected using phase shifter elements. In the phase shifter element, the yttrium gadolinium ferrite ceramic rod changes the speed at which the microwave energy passes through it, depending on the magnetic field strength induced in the coil. Due to the wave interference phenomenon achieved in this way, The direction of the transmitted beam, where the majority of the power is concentrated, is deflected. Each phase shifter element is individually controlled digitally. The RPN has around 10,000 of these phase shifters. It is worth looking back into the past to understand the essence of the concept of the RPN and why it was far more intelligent and advanced than were its predecessors. The V200 fire control radar of the S-25 Berkut, the Yo-Yo, scanned the entire 54 by 54 degree sector. This required a massive and specialized antenna system composed of 6 rotating antennas, which made it impossible to make it mobile. The Volkov system's 2 wide beam antennas measured the target azimuth and elevation in only a 7 by 7 degree large sector. In contrast, the flap-lit radar could scan with 1 degree wide pencil beams in azimuth between plus-minus 52 degrees and in elevation between 0 and 70 degrees. The radar measured the parameters of 6 targets and 12 missiles 10 times per second. Therefore, compared to the Yo-Yo radar, the zone where the target tracking was possible was far larger, but the area what was actually scanned in the same amount of time was only a fraction of it. However, the flap-lit radar did the scanning in an intelligent manner. From the perspective of missile guidance, the Yo-Yo's approach was excessive, we can call it overkill. It scanned the entire azimuth and elevation range because the mechanical scanning. In contrast, the RPN focused only on targets and the airspace around them, searching for potential separating signals, which is necessary for detecting the launch of anti-radar missiles. Compared to the Berkut, the intelligent scanning of the RPN fire control radar meant that in terms of target acquisition it had serious limits. It focused only on the designated and tracked targets and could perform independent target search only if there were free target and missile channels available. Despite this disadvantage, it far surpassed the S-75M Volkov and S-125 Neva systems, where the fire control radar scanned only a few degrees around a single tracked target. The RPN could track 6 targets, meaning it scanned 6 targets with pencil beams, but these targets could be anywhere within the 105 by 70 degree size area. This capability allowed the RPN to efficiently manage and engage multiple targets simultaneously, a significant advancement over previous systems that were limited to a much narrower field of view and only a single target. The RPN transmitted coherent quasi-continuous pulses with 4 different medium pulse repetition frequencies during target search to eliminate the issues of blind speed and blind range phenomenon of Doppler radars. The explanation of these is in the Patreon extra content. The RPN was capable of measuring not only targets' azimuth and elevation, but also its range and speed. Once a target was being tracked, the system could calculate and determine the required azimuth and elevation angles for continuous target illumination. To understand how Big Leap was ahead the RPN radar, let's just briefly review how its predecessors operated. The S-25-75-125 trio could only measure the azimuth, elevation and range. The speed was derived from these parameters. The S-75 and 125 systems could measure the speed of only one target at a time, even if other targets were visible alongside the tracked target in the narrow scan zone. The RPC of the S-200 system primarily measured only the bearing and speed of a single target, then calculated the target's position. The initial range for the calculation was provided by the P14F target acquisition radar. If it was necessary, the RPC could perform a single range measurement using phase modulation of a monochromatic signal. In contrast, the RPN radar could measure the azimuth, elevation, range and speed of 6 targets and 12 missiles with 10 Hz frequency, 10 times per second, rather than just calculating these values. This capability marked a significant leap forward in radar technology, allowing the multi-target engagement capability with a single fire control radar, which could be mobile. Let's now look at the different scan patterns of the RPN, depending on the different kind of target acquisition. If the target coordinates were forwarded from the PBU using the data of the RLO radar or from a higher level automatized command control system, the RPN scanned 4 by 4 degree area around the forwarded elevation and azimuth data. If target's coordinates were provided by the Low Altitude Target Acquisition Radar, the NVO, the RPN scanned only a 1 by 6 degree area. Acquiring target tracking was much quicker compared to the previous case. If target coordinates were received via radio speech, due to the time delay of such communication, the RPN scanned 4 by 12 degree area. The RPN was also capable of autonomous target search and acquisition. The scan was performed in a 1 by 105 degree area. The elevation of this signal bar is adjustable as it is needed. The RPN was also able to track its own missiles after launch. The radio command guidance, also the track via missile guidance, demands this feature. The radar array being PESA type was a must-have design feature for this to work. As the missile flew away, a small scanned area was sufficient for missile tracking, since the relative bearing change of the missile decreases with increasing distance. Interestingly, the RPN could track higher number of its own missiles than enemy targets. These features illustrate the RPN's flexibility and advanced functionalities, enabling efficient target acquisition and tracking in various scenarios. The RPN was able to track a MiG-21 sized target from 125 km, detection range against terrain-following cruise missiles with a radar cross-section of 0.1 square meters was 30 km. The maximum display distance was 200 km. The maximum target altitude was 27,000 meters. The RPN operated in a centimeter wavelength range in the X-band, but a shorter wavelength than the NVO. The deployment and readiness time from March was 2 hours for the S-300P and only 5 minutes for the PS, where the radar was installed on a self-propelled vehicle. The switch on time in the deployed position was 3 minutes for both variants. The first S-300 version, the PT, used radio command guidance called Remote Control 1 TU1. With the PESA type RPN radar, the S-300PT was able to guide 12 missiles at 6 targets at the same time. However, the accuracy of the radio command guidance method deteriorates with distance, which limited the range of the system to 47 km. Another important condition is that the missile channels cannot be allocated freely. No matter that the system has 12 missile channels, it is not possible to guide 3 missiles to 4 targets. Either 1 or 2 missiles can be guided on each target. If you imagine a case where 4 targets have to be downed, only 8 missiles can be used. The remaining non-utilizer track and scan time can be used for target acquisition, otherwise the scan time increment was unused. The Remote Control 2 TU2 guidance method is used by the PS version, is similar to the track via missile guidance method of the American Patriot SAM system. The basic principle of this guidance that the reflection from the target is received by both the RPN radar and the missile. This is why it is called TU2 guidance. The advantage of this method is that due to the triangulation of the target, it makes countless jamming methods ineffective, while the new type of guidance provides the accurate missile guidance beyond 47 km of distance. Because the S-300 has a modular structure, if it is required, the RPN radar also can be mounted on the 40V6M mast like the NVO. It is also possible to extend the target tracking distance of the fire control radar against low altitude targets. However, utilization of the mast increases the launch readiness time from to stop to 1 hour scale from 5 minutes for the PS variant. Now we are familiar with the radar and guidance and the background of the S-300P, the rest of the features and the capabilities of the system are a topic for another time. If you like the video, you can share, like, subscribe or ring the bell and follow the channel. You can support it via Patreon or exchange for early access, voting on planned topics and extra content and updates about the project. So far, 10 Patreon extra content has been released, their description are in the link under the video.